In this video, we're going to take a look at how to calculate the K value from an equilibrium expression. So in the type of problems you're going to see here, you're going to be given a reaction like this at equilibrium and concentrations at equilibrium. They were measured for you by the experimenter. And so to calculate the KEQ, the actual value of it, all you do is you create an equilibrium expression first, and then from there, you plug your values in and you figure out your K value. That's it. So let's go over here. We have, this is our reaction. Let's write an equilibrium expression first. So KEQ is equal to NH3 squared over N2, we should put our states, N2 gas to the power of 1 times H2 gas to the power of 3. And so now our next step is to simply plug in our numbers. So KEQ is equal to 0.30 squared over, oops, I chose those numbers without looking properly. You got to be careful. So NH3 is here, 0.20 squared over, so N2 is 0.30 to the power of just 1. And then H2 is 0.10 cubed. And so we can go ahead and plug that into our calculator and see the result that we get. I highly recommend you practice using your calculator during these rounds to make sure that you are on the right path with using your calculator properly. So I have mine ready, 0.2 squared divided by 0.3 divided by 0.10 to the power of 3. And we get 133.333, which we could, to the proper number of sig figs, 2 sig figs, is about 130. Notice I didn't use units because we don't really report K values with units, so I didn't even include them into the calculation. This is the one rare exception where you don't have to do that, okay? We can make a conclusion here. We see that K is greater than 1, right, because it's 130. Therefore, the products are favored. Concentration of products should be greater than the concentration of reactants at equilibrium. So the products are favored at equilibrium in this situation. And so that's how you calculate a KEQ. Let's go try the next example. So you can try this one on your own. Read the question carefully. So we have a reaction here. And we gave you a bunch of equilibrium concentrations. And we actually want you to find the equilibrium concentration of water vapor in this situation. So we have the K given to you, but you have to find water vapor's concentration at equilibrium. That's a very useful tool or thing that the K value provides is if you know the K value and you know concentrations at equilibrium for a variety of things, whatever you don't have the concentration for, you can calculate. So first step is let's write a K expression. So KEQ, or K, that works as well, is equal to CO, gas, to the power of 1, times H2, gas, to the power of 3, over CH4. We can do this because they're gas, they're not solid or liquid, times H2O, which is our X. And what you're doing is you're basically rearranging to find H2O. So you're sending this to this side and the other, and KQ down to the bottom. So our concentration of H2O gas is going to be equal to the concentration of CO gas times H2 gas cubed over CH4 gas times KEQ. And so we can just plug our numbers in now. So the concentration of H2O gas is equal to, so let's see, CO is 0.300 times H2, which is 0.800 cubed, over CH4, which is 0.400 times the 5.67. It looks like my smallest number of sig figs is 3. So when I put my final answer, it'll be to 3 sig figs. So let's go ahead and figure that out. So 0.8 cubed times 0.3 divided by 0.4 divided by 5.67. And it looks like I get, and you should try this too, remember you're pausing and trying, 0.06772, but I suppose I would leave it at 3 sig figs. Now be careful, I did say that units are not reported for K. This is the concentration of water gas, and it's a concentration. You do have to report units, and you just use the same units that are in the question. So concentrations here are in moles per liter, so you could put big M over here. So this is our concentration of H2O in this particular situation. Okay. So we're going to try one more example. This is a bit of a different type of question. You'll see there's a bit more to it, but overall, still very similar. So at a particular temperature, a 3-liter flask contains 2.4 moles of chlorine and 1.0 moles of nitrosyl chloride, and then 4.5 times 10 to the power of negative 3 moles of nitric oxide. Calculate the equilibrium constant given the balanced equation. Determine what is favored in this equilibrium and explain how you know. So first, I'm going to start off with what you're all kind of used to. Write in that K expression, K equilibrium. And so we're going to have our Cl2, concentration of that. Not squared, it's just the power of 1, times NO, concentration of that. That one squared because there's a 2 in the front. Over this NOCl gas to the power of 2. And so generally, you'd go in and you'd plug in your numbers. You'd plug in your 2.4 moles of chlorine, your 1 mole of this NOCl, and your 4.5 times 10 to the power of 3, negative 3 moles of nitric oxide. But remember that moles are not concentrations. This needs to be concentrations, because that's what an equilibrium looks at, change in concentration over time. So before you can actually go and plug all this in, you actually need to go and find the concentration of everything. So your little side mission, let's call it step 1.5, before you go to the last step, step 2, which is plugging everything in, is to find the different concentrations. So remember that C is equal to N over V. So if you want to find the concentration of chlorine, you have 2.4 moles divided by 3.0 liters, right? Because that's your 3-liter flask. If you want to find your concentration of, let's say our next reactant is nitric oxide, you do your 4.5 times 10 to the power of, let's do that. So concentration of nitric oxide, you do your 4.5 times 10 to the power of negative 3 divided by 3.0 liters. It'll be moles per liter soon. And then lastly, your concentration of NOCl will be 1.0 moles divided by 3.0 liters. And so you're just trying to find your concentrations so you can plug them into your equilibrium expression. So we'll have 2.4 divided by 3, and we'll get 0.8 molar. We'll do 4.5 times 10 to the power of negative 3 divided by 3 gives you 0.0015 molar. And then lastly, you have your 1 divided by 3, and you get 0.333, so on and so forth, molar. So now we have our concentrations, and now we can go plug those in. So we'll have 0.8 molar times 0.0015 squared over 0.3333, so on and so forth, squared. Try not to round too much. Try to keep some decimal places there so that you're not too far off from the question in the end. So let's go ahead and do that. So we have 0.0015. We'll square that times 0.8 divided by 0.33333333 squared. And you'll see that you'll get this number here. You can write it in scientific notation if you'd like, but make sure you have the same number as me. So 0.0000162. So it's 400,162. Now, just to take a look, it looks like 2 sig figs is what we're at. So we're going to be looking at about 0.00016, or you could say 1.6 times 10 to the power of negative 5. So this is your equilibrium expression. The last part, so we have, let's see, we have our expression here, we have our constant we calculated here, but before we could do that, we could find the concentrations. The last part is simply asking what's favored at equilibrium. Well, notice that the K value is less than 1, much less than 1. Therefore, the reactants are favored over the products at equilibrium. And that's because, so reactants favored. And so in this video, what did we see? We saw how to calculate equilibrium constants by making equilibrium expressions for various systems and then simply plugging in concentration values. It's important you keep an eye out for things like the states because if you had liquids and solids, it would not be included. Also important you keep an eye out to see if you were given the concentration or if you were given the mole values. Because if you were only given the mole values, then your equilibrium expression and constant would be off. You have to make sure you convert those mole values into concentration by using your C is equal to N over V. In the next video, we're just going to do a quick overview of the different types of equilibria that exist because our unit will basically consist of studying different types of equilibria.